In the tutorial, I am going to explain how to solve the focused questions for the 12 Advanced End of Term 1 exam. Let's first begin with topic 1.1. A fruit contains 1,400 calories. How much joules and kilojoules does this fruit contain? You have to note that in your exam, you are going to have a formula sheet that explains, that shows you that 1 calories is equal to 4.18 joules. So now I have 1,400 calories. So 1,400 calories is going to be equal to times 4.18, and like this I'm gonna get how many in joules. So 1,400 times 4.18, that is equal to 5,852 joules. Now to convert from joules to kilojoules, from joules to kilojoules, we divide by 1,000. Whereas if I am converting from kilojoules to joules, I can multiply by 1,000. So the answer in kilojoules is going to be 5.852 kilojoules. Moving on, room temperature is defined as 25 degrees Celsius. Convert this temperature into Kelvin. Please note that the conversion factors of temperature are also given in your formula sheet. So, to convert from Celsius to Kelvin, we add 273. Whereas to convert from Kelvin to Celsius, we subtract 273. Now, having this temperature in Celsius, we're gonna add to it 273, and the answer is gonna be 298 Kelvin. This is how I convert Celsius to Kelvin. Another one, absolute zero is defined as 0 Kelvin. Convert this temperature into Celsius. So as I mentioned here, from Kelvin to Celsius, you subtract 273. So 0 minus 273, and the answer is going to be negative 273 Celsius. Now let's move on to more conversion factors. There's one thing you have to pay attention, the way they write the unit calorie. There's capital C and there's a small c. If it's written capital C, it means that is kilocalories. So when they give you this, you just have to convert it. So first of all, I have in my question the 250 that is in calorie, which is in kilocalories. I need to convert it to joules. So first of all, I'm gonna convert it to calorie, then from calorie to joule. So again, I'm gonna put the conversion factors over here. From kilocalories to calories, you multiply by 1,000. From calories to kilocalories, you divide by 1,000. So I'm gonna need only the first one, from kilocalorie to calories. Now, also, 1 calorie is equal to 4.18 joules. So after I convert to calories, I'm gonna convert it to joules. So this 250, first of all, I'm gonna multiply it by 1,000. Now I converted it to calories. And then again, I'm gonna multiply it by 4.18 in order to get it to joules. So 4.18, and that's 1,000. So the final answer is 10,000. So it's with the significant figures. I'm gonna write it 1.045 times 10 to the power 1, 2, 3, 4, 5, 6. So joules. Let's continue. 375 kilojoules to calories. So, first of all, I'm gonna convert from kilojoules to joules, and then from joules to calorie. That's the plan. I'm gonna write it in a smaller way. So, my plan here to do the conversions is to convert the kilojoules to joules, and then from joules to calories. Why I chose to remove the kilo? Because in my conversion factor, I have from calorie to joule and not from kilojoules. So, again, to convert from kilojoules to joules, we multiply by 1,000. And to convert from joules to calories, we have to divide by 4.18. Okay? So from joules to calories, we divide by 4.18. So here, that's my final answer is going to be 8.97 times 10 to the power 234 calories. Now, part C, convert from calories to kilojoule. Let me put a plan for this. First, I'll convert calories to joules, then from joules to kilojoules. So, 400, I'm gonna do it over here, 420 calorie, to take it to joule, I am going to multiply by 4.18. Now it became in joules. Now from joule to kilojoules, I am going to divide by 1,000. And the final answer is going to be 420 times 4.18 over 1,000. That is 1.76 kilojoule. So remember this. I'm going to write it in a simpler way. If you are converting from calories to joules, you multiply by 4.18. If you are converting from joules to calories, you divide by 4.18. If you are converting from calories to kilocalories, which is capital C cal, you divide by 1,000. If you are converting from kilocalories to calories, you multiply by 1,000. Same thing, if you are going from joules to kilojoules, you divide by 1,000, and from kilojoules to joules, you multiply by 1,000. Now another question, the temperature of a sample is 300 Kelvin. What is the temperature in Celsius? To go from Kelvin to Celsius, we subtract 273. So the answer is 27 degrees Celsius. So the metals below with the specific heat capacities are gold, 0.129 joule per Celsius gram, copper 0.385, and silver 0.235. 3 samples of equal masses of each substance initially at the same temperature are heated equally. So we are giving the same amount of heat to every type of metal, knowing that these metals are with the same mass and they were heated for the same amount of time. Arrange the samples by increasing the final temperature and explain your answer. You have to know that the specific heat capacity, C, is the amount of heat needed to increase the temperature of a substance. So for example, if I look at gold, gold has a 0.121 specific heat capacity. It means to raise the temperature of gold 1 degree Celsius, we only need 129 joules of energy. Whereas if I want to raise the temperature, so that's the goal. So if I want to raise the temperature of copper, for example, I need more amount of energy to raise the temperature of copper by 1 degree Celsius. So if these three metals were heated for the same time and they were given the same amount of heat, gold is going to increase its temperature a lot because it doesn't require energy as much as copper does. And therefore, based on this, I can arrange them. So the one that is going to change its final temperature, or the one that's going to have the highest final temperature, is the one that changed a lot, and that is gold. The one that is going to have the lowest final temperature, because it couldn't change a lot, that is going to be the copper. And finally, silver goes in the middle. You need to understand that temperature change and specific heat capacity are indirectly proportional. The specific heat, the temperature changes a lot, so it's a big change. I'm just going to erase this to provide space. So temperature changes the most when the specific heat capacity is the least. So that's the relationship between the temperature change and the specific heat capacity. Moving on with our question. 200-gram blocks A and B. And as you can see, the specific heat capacities are different. A has a larger specific heat capacity than B. They absorb the same amount of energy. Which block will have the greater change in temperature? So again, I'm going to show you. A needs a lot of energy, 0.90 joules for every gram to just increase 1 degree Celsius. Whereas for B, it doesn't need this much. It only needs 0.39 joules to increase 1 degree Celsius an amount of 1 gram. Therefore, which gonna change a lot? The one that requires less energy. So B, if I heated A and B for the same amount of time, B will change its temperature more, or will experience the biggest change in temperature, will experience a bigger change in temperature compared to A. And that is because B has the lowest specific heat capacity. You need to mention that in your answer. Moving on. 100-gram sample of water in a beaker and 100-gram sample of metal. So 100-gram sample of water and 100-gram sample of metal. Each of them absorb 500 joules. In a flask, each absorb 500 joules of heat. So I'm going to highlight this in 2 colors because both of them, they absorb the same amount of heat. Now, the specific heat capacity of water is 4.18 and that of aluminium 0.90 joule per gram Celsius. Find the temperature change of each and explain your answer. Now, there is one formula that we use in this lesson, which is Q equal MC delta T. They want us to find the temperature change. Delta means change. They want us to find delta T for aluminium and delta T for the water. So I'm gonna start for water. What do we have? Q of water is 500 because both of them, they had the same Q. So Q of water is 500. Mass of water is 100. Specific heat capacity of water is 4.18. And now delta T, the one that we are checking it to find it. So the temperature change. Therefore, the temperature change is going to be equal to 1.2 degrees Celsius. Now, for aluminum. The mass of aluminum is 100 grams. And aluminum also absorbed 500 joules of energy. But the specific heat of aluminum is 0.90, and we are finding the temperature change. And the temperature change is 5.6. Now let's look at the information, our answer. Is it logic? Let's see. The water has a higher specific heat capacity. It didn't change a lot. Whereas the metal that has a lower specific heat capacity, it changed more. So yes, the biggest change in temperature goes to the metal aluminum. Let's continue. If the specific heat capacity of gold is 0.129, how much heat will be absorbed if 29 gram sample of gold heated from 10 to 100? Whenever you are reading a question, please highlight the given. This is the specific heat capacity of gold. Understand your unit. 29 gram, that is a mass. And then it says heated from 2. From 2. So, Q equal MC delta T. They want us to find how much heat, the Q. So, the mass is 29 grams. So, the mass is Q equal 29 grams. The specific heat capacity of gold is given. Now, delta T, always remember the delta is final minus initial. So, go back and read. The temperature changed from 10 to 100. So, it means 100 was the last temperature and 10 was the initial temperature. By entering this to your calculator, you get a 336.69 joules of energy absorbed. Let's continue. The specific heat of silver is given. From the unit, I know that this is a specific heat capacity. How many joules of heat? Q. How many? The Q. They want me to find Q. Is absorbed by 30 grams of silver if it is heated from 20 to 40. So, this is the formula. They want me to find the Q. That's the mass. That's the specific heat capacity. And it absorbed. So definitely the temperature is going to raise. And absorb, it means my answer is going to be positive because heat is absorbed. Final minus initial. So my final answer is going to be 231 joules. Another question. A 75 gram of sample, that's mass, is heated from 2 initial to final. And that's the C of water. Calculate Q. So again, how do I calculate Q? Q equal MC delta T. So Q equal, the mass is 75. The specific heat capacity of water is 4.18. Final minus initial temperature. Be careful. most of the students, they do mistakes and they write T initial minus T final. That's a delta, final minus initial. So the answer is 1.74 times 10 to the power 4 joules of heat absorbed. Again, another question. 120 gram sample of iron cools from 95 to 25. If the temperature is going to drop from 95 to 25, it means that this sample is going to release energy. And indeed, the question, it says, calculate the amount of heat released by the iron, and they gave me the specific heat capacity of the iron. So expect here a negative value for Q, because heat is released, not absorbed. So Q equal MC delta T. The mass of that sample is 120. 0.449 is the specific heat capacity. And the temperature, this is initial, this is final. So 25 minus 95. And the answer is negative 3,771.6 joule. The sign minus indicates that heat was released. That's what it means. Now let's continue. A sample of granite that has a mass of 12 grams. 12 grams, that's the mass. Absorbs 144 joules. When they tell me absorb 144, it means that this value is positive. The Q is positive. If the temperature of the sample changes by, they gave me the delta T. They didn't tell me it was this much and turned to that number. They simply gave me the change. It changed by 15 degrees. During this change, what is the specific heat of granite? Now, because the heat was absorbed, it means that the temperature increased. So this delta T change is positive, not negative. So Q equal MC delta T. So 144, why? Because heat is absorbed, equal 12 gram is the mass, and we need to calculate the specific heat of granite, and here's the 15 degrees Celsius. So the final answer in this case is going to be 0.8 joule per gram Celsius. Definitely, the specific heat capacity is not allowed to be a negative value. 100-gram piece of a certain material cools from 90 to 30. So I would like to draw your attention here that the temperature dropped from 90 to 30 degrees Celsius. And this means that heat must be released. And here they said releasing 1.26 times 10 to the power of 4 joules. So here you need to know that Q in this is negative because heat is released. Now, what is the specific heat capacity of the material? So Q equal MC delta T. So let's substitute and see. Since they said heat is released, you have to be careful to those words. When it says released or loses heat, you have to add a negative to the Q given to you. Negative sign. So the mass is 100 grams. We need to find the specific heat capacity, and they are saying that the temperature changed from 90, that's initially, to 30. So I can know that because the temperature dropped, heat is going to be released. So 30 minus 90. So the final answer is going to be times 100. It's going to be the final answer is going to be 2.10 joules per gram Celsius. That is the specific heat capacity. Now moving on to topic 1.2. A metal with a mass of 50 grams at 100 degrees Celsius is dropped into 200 grams of water with a specific heat capacity 4.18 joules per gram Celsius, and the temperature of water is 20. Now the final temperature. When you drop a metal in water, they first both have different initial temperatures, but after they exchange heat, they're gonna get the same final temperature. They want us to calculate the specific heat capacity of the metal. Now, I always advise my students to put a table, one for metal and one for water. And in this table, they're gonna put the components of the formula of Q equal MC delta T. So the M, the C, the T initial, the T final. Okay? So the mass of the metal is given to you 50 grams. The mass of the water is given to you 200 grams. The specific heat capacity of the metal is unknown, but that of water is 4.18 joules per gram Celsius. The metal initially was at 100 degrees Celsius, while the water initially was at 20 degrees Celsius. And when they exchanged heat, when the heat was transferred from the metal to the water, why? Because the metal was hot, more hot than water, the final temperature was 24 degrees Celsius, but this final temperature is for both. Now, you have to know that the amount of heat released by the metal is the amount of heat released by the water. It means Q of metal lost is equal to the amount of energy gained by the water. So now, wherever heat was lost by the metal, it's the same gained by the water. So I'm gonna substitute. There's a minus here at the beginning. Mass of metal times specific heat capacity of metal multiplied by T final minus T initial. So 24 minus 100 equal. Now I'm reaching the Q of water. Mass of water, specific heat capacity of water, and T final minus T initial of water. 24 minus 20. And then you start solving. Once you finish solving, you'll get the specific heat capacity of the metal is 0.88 joules per gram Celsius. Again, a 50, always highlight. I advise you to highlight to separate the values for the metals and the values for the water. A 50 gram sample metal at 100 degrees Celsius is placed in 100 grams of water at 25 degrees Celsius. Assuming no heat loss to the surrounding, calculate the final temperature. The final temperature, I'm gonna put it in a different color because it's the same for both. The specific heat capacity of the metal is 1.83 and the specific heat capacity of water is 4.18. Now let's start. So let's put the table like this so that you'll know what you have. That's the metal and that's the water. M, C, T initial, and T final. So the mass of metal is 50 grams. The initial temperature of metal is 100. We don't know the final temperature, but the final temperature is the same for both, just to let you know. Now, the mass of water is 100 grams of water. We know the specific heat capacity of the water to be 4.18 joule per gram Celsius. And also the specific heat capacity of the metal is 1.83 joules per gram Celsius. The water initially was at 25 degrees Celsius. And we need to find the same initial final temperature. Now, the temperature, the heat lost from the metal is equal to the heat gained by the water. So I can say that Q, energy lost by metal, is the same energy gained by the water. So let's put the information and substitute. So in each one, MC delta T. So that's the negative. I have 50 grams mass of the metal times 1.83 specific heat capacity of the metal times T final, which is unknown, minus T initial. So TF minus 100 degrees Celsius. That's for Q metal. Here it is. That is Q metal. Now, equal. Now I'm going to start substituting for water. Q equal MC delta T. So the mass of water is 100 grams. The specific heat capacity of water is 4.18. And the temperature is T final minus T initial. T final, I don't know it. And minus T initial, that's 25. So now, here's the data information for the water. By solving this equation, we get the T final to be 38.5 degrees Celsius. If you need more practice, check my YouTube video about specifically this KPI. 150 grams piece of metal. 150 grams piece of metal is heated to 95 and then placed in water. The water is at 20 degrees Celsius. The final temperature is always for both. The final temperature is 25 degrees Celsius. Now let me continue to see what else data I have. They want me to find the mass of water, but they gave me the specific heat capacity of water, and they gave me the specific heat capacity of the metal. So let's put our table again. That's the metal, and so that's the metal, and here for the water, M, C, T initial, and T final. So mass of metal, 100 grams. Initial temperature of the metal, 95. Initial temperature of water, 20. Final temperature is 25 for both. Now, specific heat capacity of water, 4.18 joule per gram Celsius, and that of the metal, 0.40 joule per gram Celsius. So, 0.40 joules per gram Celsius. This is the unknown. So, the heat lost by the metal is equal to the heat gained by the water. So whatever heat lost from the metal is going to go to the water. So I can write this formula. Heat metal equal Q water. But the heat is going to be lost by the metal, gained by the water. So let's start to substitute. Mass of the metal, 150. First, there is a minus here. 150 multiplied MC delta T, which is T final minus T initial. That is for the metal. It's over here. Now, equal. Now, for the water, I don't know the mass of the water. That's what I have to calculate. The specific heat capacity of water, 4.18, and T final, 25, minus T initial of water. So that is the data information for the water. Now, solving this, we get the final answer to be mass of water 201 gram. Next, 150 gram metal block. Look at the metal block, it's over here. Is heated to 120 degrees Celsius, then it was dropped in a coffee cup calorimeter. The coffee cup calorimeter, so this is for the metal. The coffee cup calorimeter containing 100 grams of water at 25 degrees Celsius. That's the temperature of water. Now, after they transfer their heat, their final temperature is 38. Now, true or false? Water is the surrounding. Water is not the surrounding. The heat is going to flow from the metal to the water. The whole thing is a system. Water is part of that system. Metal is a system, yes, and water is a system. Water gained heat to raise its temperature. Yes, the temperature of the metal temperature is 120 degrees Celsius. That is very hot. So it's going to transfer its heat to the water. So the temperature of the metal is going to drop. The temperature of the water is going to increase. You can also draw it. I had a metal of 120 Celsius and I had water of 25 degrees Celsius. This dropped and this increased until both now are 38 degrees Celsius. So water gained heat and water temperature increased. That is correct. Moving on. So these questions are about system and surrounding. So during a lab experiment, a student reacts a piece of magnesium with a dilute solution of hydrochloric acid, as you can see here in the figure, in a conical flask. Fine. The reaction releases heat to the surrounding. So here's the system. Here is the system, which is the HCl and the magnesium ribbon that is releasing heat to the surrounding. Which of the following is the system? So the HCl solution and the magnesium ribbon. Which of the following is the surrounding? Everything else, which is the conical flask, the lab room, the lab experiment room is a surrounding, the student is a surrounding. So the place where this experiment is going on is the surrounding. I don't know what I wrote here. It's conical flask, I should write. Okay. Now, this reaction is what? This reaction, this system released heat. So this system is exothermic. And plus, if I come and I touch the conical flask, it's going to feel hot to touching. And that is one of the characteristics of exothermic systems. When it releases heat and you touch it, you being a surrounding, you're going to feel it's hot. If we calculate the enthalpy change of an exothermic system, it's always a negative value. So it has a negative sign. Now, energy diagrams of endothermic and exothermic, this plays an important role in your end of term exam. Now, let's look at this diagram. This diagram starts at 100, increases up to 250, and then start releasing energy, but it releases more than it was. It releases and the final energy becomes 50. Now, because the heat absorbed is less than the heat released, this diagram belongs to an exothermic reaction. Another indication, it starts at 100 and the enthalpy of reactant is 100. The enthalpy of product is 50. So the product is less, so it's an exothermic reaction. Let's start reading the question. What is the value of enthalpy of the reactant? Here are the reactants. So the enthalpy of reactants is 100 kilojoules. What is the value of the enthalpy of the product? The product of the backward reaction. If they are talking about a backward reaction, so it's going to start from here, go up, 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 and then stops at 100. So the product, again, for the backward is product kilojoule of backward. If they said the product of forward, I would say 50. On the diagram of this question, label the activation energy. Activation energy is the energy needed to activate this reaction, to reach the peak of this curve, which is called activated complex. Activated complex. So the activation energy is this amount of energy needed. So the reactants, they need to absorb this much of energy so that the reaction is activated. So this is the activation energy. So you must draw this arrow on your graph to show your answer. On the diagram, label the delta H of the reaction and write down the value. Delta H is the difference between enthalpy of product minus enthalpy of reactants. Final minus initial. So it's 50 minus 100. So that is delta H, only this value. And when I do 50 minus 100, I'm going to get a negative value. So here they asked me to draw it and write its value. So the enthalpy of this reaction is negative 50 kilojoules. For the diagram in question 18, is the forward reaction endothermic or exothermic? Didn't we get delta H to be negative 50 kilojoule? Isn't it delta H negative? It means releases energy. So it means that this reaction is exothermic. And when they tell me justify, because heat is released. Heat is released. I can also say because delta H is negative. And also I can justify by saying the enthalpy of product is lower than the enthalpy of reactant. So all of these are accepted justifications. Another question. Label the activated complex and the enthalpy change of the reaction of the forward. Okay, so let's label the activated complex. Activated complex is the top of the diagram. So here is called the activated complex. It's an unstable structure that is like a preparation to shift from reactants to products. It's where the old bonds are broken and new bonds are preparing to form. Now for the enthalpy change, of the reaction, it's the difference between the enthalpy of product minus the enthalpy of reactant. So it's only this portion. That's the difference. That is delta H. Another question, they want me to mention whether this is endothermic or exothermic. Now, we absorbed more than what was released, or enthalpy of product is higher than enthalpy of reactants. Or even if I want to calculate delta H, it's 160 minus 80, it's a positive value. So for all these reasons, I would say that this reaction is endothermic because the delta H is positive, or because the enthalpy of reactant is less than the enthalpy of product, or because energy absorbed is more than the energy released. What is the value of the activation energy? Note that this is the activated complex. Activation energy is the energy needed from the reactant to reach the activated complex. That is the activation energy. It's from 100 to 400, so the activation energy is 300 kilojoules. Moving on. Given the below thermochemical equations, so I'm looking at this one, I see a combustion reaction, and I see a negative delta H written next to the equation. Is the reaction above exothermic or endothermic? Since the value of delta H is negative, or because this is a combustion reaction, I can say that this reaction is exothermic. Now, let's compare the given equation to solve 26. Here we go. C2H5OH, C2H5OH. But now it is multiplied by 4. Before it was 1. And this 3 was multiplied by 4, it turned to 12. And this 2 was multiplied by 4, it turned to 8. And this 3 by 4, it turned to 12. So what we actually did, we just multiplied this equation by 4 to get this one. So the delta H is going to be simply this value by 4, which is equal to negative 5,468 kilojoules. Now, again, let's compare it one more time. This one, C2H5OH, is still here, but the one that is here became 3. The 3 here became 9. It was multiplied by 3. The 2 times the 3 is 6. The 3 times the 3, 9. So what we did, we just took the given equation and we multiplied it by 3. So what would be the delta H? Simply the value by 3 kilojoules. Let's continue. Write a thermochemical equation for the combustion. Combustion. Whenever they tell you combustion, it means you add oxygen to the given compound. So combustion of C6H12 producing carbon dioxide. Carbon dioxide is CO2 and water, H2O. The product of combustion are always the same. We always obtain CO2 and H2O. Indicating the sign of delta H and identifying if it's exo or endo. Any combustion reaction is always exothermic. So I'm going to write C6H12, that's a gas. That's a gas. It was added to oxygen. Oxygen is a gas. And upon combustion, we got carbon dioxide and water, but it's in the vapor phase, gas. So the delta H of this one is going to be negative. Now I still need to balance. I have 6 carbons, so I'm going to write over here 6. And by writing 6, now I have 6 carbons and 12 O just from here. Now, I have 12 hydrogens, so I'm going to multiply this by 6 to get 12 hydrogens. 6 times 2, 12. Now, for the oxygen, I have 12 oxygen coming from this and 6 coming from this one. Therefore, I have a total of 18 oxygens. So, I'll put 9 here because 9 times 2 equal 18. Just for your information, in a combustion reaction, O2 and a reactant, CO2 and H2O in the product are always fixed. We always get them. What changes is the given formula in the question, whatever they give you. See, again, here's another question. Thermochemical equation for the combustion of C5H12. So instead of C6H12, now we have C5H12. What are we going to get? This is the O2. I told you it's fixed. I always get CO2 and H2O because this is a combustion. So CO2 and H2O. And I need to balance it. 5 carbons, I'm gonna write here 5. 12 hydrogens, I'm gonna write here 6, and I am done. That's it. Define the molar heat of vaporization and write a thermochemical equation. The molar heat of vaporization, the molar enthalpy of vaporization is the amount of heat, of energy. Now, what is vaporization? Vaporization means you are going from liquid to gas. So it's the amount of heat needed, absorbed, required, absorbed for, since they said molar, so you're gonna say for a 1 mole of a liquid to change to gas at a constant temperature, because when the change starts, the phase change of liquid turning into gas, at that point the temperature stays the same. Now, because I said that heat is absorbed, this kind of change is endothermic. And it will have a delta H, it will have a delta H that is positive. So I'm gonna write the equation. Just take any example. H2O liquid going into H2O gas. H2O liquid to H2O gas, and you write next to it delta H is a positive value. Or you can simply write H2O, sorry for this, so you can simply write H2O, here we go, liquid plus heat gives H2O gas. So this is the thermochemical equation. Now again, define the molar enthalpy of fusion, after it of condensation, after it of solidification. You need to know all of these. So I'm gonna write the same definition and I'll tell you what do I change. Molar heat, so before doing that, let's see, what is fusion? Fusion is when a solid changes to liquid, it's melting. Condensation, when a gas changes to liquid. Solidification, when a liquid changes to solid. So here, molar enthalpy of fusion is the amount of heat, I'm gonna put some space, by 1 mole of a substance to change from to at a constant temperature. Okay? That is the same sentence. You are going to put it in the 3. And the amount is the amount of heat by 1 mole of a substance to change from to at a constant temperature. Again, is the amount of heat by 1 mole of a substance to change from to at a constant temperature. Now let's put the missing. Fusion, to change from solid to liquid. When a solid goes to liquid, it absorbs energy. So it's the amount of heat absorbed. Condensation. Condensation, it's the change from gas back to liquid. So for a gas to go back to liquid, it must release. So it's the amount of heat released by 1 mole of a substance to change from a gas to liquid. Solidification, it's a liquid that has to change to solid. And the liquid, to go to solid, it's going to release heat in order to turn into solid. So think about it this way. Same thing for the vaporization as well. I can say molar enthalpy of vaporization. What is vaporization? It's to change from liquid to gas. So it's a heat absorbed for the liquid to go to gas. So, and fusion is of solid to go to liquid. Always think about it this way. Solid, liquid, gas. Solid to go to liquid and liquid to go to gas, energy is absorbed. Now, gas to go back to liquid or liquid to go back to solid, energy is released. So let's think about it. Vaporization, that's liquid to gas. Heat is absorbed during vaporization. That's correct. Fusion is solid to liquid. Again, fusion is absorbed. Yeah, so that's the correct answer. Which is the correct about the molar enthalpy of condensation and solidification? Okay, hold on. Condensation is gas to liquid. Solidification, liquid to solid. So let's think about it again. That's SLG, energy absorbed, and down here, energy released. To change from gas to liquid, here, energy is released. So in the condensation, energy is released. In the solidification, liquid to solid, again energy is released, liquid to solid. So yes, energy is released. So the answer is A. Perform calculations with those phase changes. And trust me, they're really easy. You just have to understand the unit. The enthalpy of vaporization is 40.7 kilojoule per mole. It means for 1 mole. How much heat is required to vaporize 3? So it's going to be 40.7 multiplied by 3. And that is 122. Again, another question. In a laboratory experiment, 5 moles of ice melted at 0 degrees Celsius. Given the heat of a fusion of ice is 6.01 kilojoule per mole. It means for 1 mole. What would be the heat of a fusion or the energy absorbed if I have 5? So it's going to be 6.01 times 5, and that is 30.1 kilojoules. Hess's law. For Hess's law, there is a video tutorial on my channel that will help you also learn more about Hess's law. In Hess's law, you always have a target equation and you have given equations. I'm going to name this equation 1 and equation 2. And you need to manipulate those given equations in order to find or to reach the target equation. So the best way to do this is to find the given in the target and search for it. For example, 2a, I will search for it in the two given equations. So here I want to look for 2a, and I can find it in 1. I want a next to it 2, there is 2 not next to it. And I want a to be in the reactant side, and it is in the reactant side. So equation 1, keep it the same. So equation 1, keep it the same. And you write it again. C2, A2, C3. So delta H will remain the same. I didn't do anything. Kilojoules. I'm done with this. Now let's look for B2C3. Where do I find it? Here it is. It's in B. Okay, but I want B2C3 on the reactant side, and in 2 it's not on the reactant side. So I will say that equation 2, flip it or reverse it. So B2C3, this one is going to become like that, giving 2B and 3/2 C2. Now since you flipped this equation, definitely you're going to flip the sign. 285 kilojoules. Finally, I've reached the target. The delta H of the target reaction is the sum of these two. So negative 1087, 874, and 285. So the final answer is negative 1589 kilojoules. One more question. Here's my target equation. And I need to manipulate the given equations, equation A and equation B, in order to reach the target. So let's search one by one. Let's first find HCl. Here's HCl. It's over here. Yeah, but I want HCl on the reactant side. You see, here's the arrow. I want it on the reactant side. So first of all, I'm going to flip A. So when flipping A, I'm going to get 2HCl, H2, and Cl2. But that's not all. I also need next to HCl 4, but instead of that, I have 2. So I'm going to flip, and I'm going to multiply by 2. So what I'm going to do here, by 2, that means becomes 4, by 2, and by 2. Now what happens to the delta H? You flipped it, so it becomes positive, and you multiplied the equation by 2, so you need to multiply the delta H by 2. That's what should be done. So the answer of this one is going to be 370 kilojoule. Now I'm done with A. Let's move on. Oxygen, O2. Where do I find it? I find it in A. It's right here. That's O2. And it's in the right position as a reactant, and there's no need to multiply it by anything. So B stays the same. Now, because B stays the same, you still have to write it, because that's a part of your answer. So 2H2 plus O2 gives 2H2O. And I didn't do anything to this, so this remains the same. Now, to find the final answer, I hope that it saved. It didn't save. So to find the final answer, I must add these two delta H's. So again, I'm going to tell you, I flipped this and I multiplied it by 2. So the delta H was flipped and it was multiplied by 2. The answer was 370 kilojoule. And this one, I kept it the same. So the delta H, I didn't change it. So Finally, to find the delta H of this whole equation, you add the two values, 370 and negative 483.7. And the final answer is negative 113.7 kilojoule. That's an exothermic one. Let's do another example. Here's the target equation. And I have 4 given equations. I'm gonna call this A, B, C, and D. And I'm gonna find one by one in the equations to see what I am going to do. So let's start with CH4. Let's search for it. Here's the CH4. I need to flip B because I want it on the other side. And I need to multiply B by 2 because I need 2 next to it. So it's going to become 2CH4, 2C, and 4 hydrogens. So this value over here, you're going to flip it times 2. So it's going to become positive and times 2. Now, I'm done with B. Let's move on to NH3. Where is it? Here is NH3. I want it on the reactant side. Be careful, here's the arrow. I want it on the reactant side, so I'm gonna flip A. But there is 2 next to it, already there's 2. So just flip A. So 2 NH3, N2, and 3H2. Now for this, I'm gonna flip it. And I'm done with A. Now O2. O2. Now I'm here. Where can I find O2? I find it here in D. So I'm gonna multiply D by 3. So D, multiply it by 3. So 2 times 3 times 3 times 3. So it's gonna be 6H2 and 3O2 and 6H2O. So I only multiplied this by 3. So this value over here, I'm gonna multiply it by 3. I'm done with O2. Now let's move on to HCN. Where is it? Here it is. And it is exactly like I wanted. So C stays the same. So I didn't do anything to this value. It remains the same. Now, the final answer, you add them all. You add them all. And you get this as a correct answer. We reached the part in our revision session where we need to use the summation equation to calculate the standard enthalpy change of a reaction. And that is always given to you in your exam. It's the summation of the enthalpies of formation of products minus the summation of the enthalpies of reactants. You can also check on my channel. I have a separate video for applying this formula. Now, when you read an equation, my advice to you, highlight the reactants with a color and then highlight the products with a different color so that you know what you're doing. Now, let's start finding the enthalpy, the sum, the total enthalpy of reactants. So I have this one, C2H2 gas, it is 226.7, and there is the hydrogen, and the one for hydrogen is 0 because it's a standard element. So the enthalpy of formation of reactants is 226.7 kilojoule per mole. I get the unit from the question. Now, let's do the one, so that was for reactant. Now let's do the one formation of product. I only have here one product, it is C2H4, and that is 52.3. So it is 52.3 kilojoule per mole. Now when it comes to calculating the enthalpy change of the reaction, we take the products, minus the reactants, final minus initial. And the answer is negative 174.4 kilojoule per mole, because that's a standard. I have more practice exercises to help you better understand this. So here's a question. I'm gonna solve it in 2 ways. And you get to choose the one that suits you. So I have here this equation. There's a very simple way. You just substitute every formula with the enthalpy of formation. Like for example, P4O6 is negative 1400.1. And then there's plus, then there's 2 multiplied by the 0. That's the oxygen. It is 0, but you do have to mention it and show it in the substitution formula. P4O10 is this one, so negative 2984.0. Now let's solve this. It's 1000.1 and this one. Now, enthalpy of the reaction, it is final minus initial. So, final minus initial. And the final answer is negative 1343.9 kilojoule per mole. Now, let's do it in a different way. It's not a lot different, but it is the one that you calculate the enthalpy of formation of product separately, the summation of enthalpy of formation of reactants separately, and then the one that you get the enthalpy of the reaction. So, product, I'm going to highlight it in blue. Here's the product. It is P4O10. So it's negative 2984 kilojoule. That's the only one in the product, so we're done with the product. Now the reactant, I have 2 reactants, these two. So what I'm gonna do is the following. Negative 1640.1 plus 2 multiplied by 0, which is negative 1640.1 kilojoule per mole. I'm done with the reactants. Now, let's get their change. The enthalpy of the reaction, it's the products minus the reactant. We get the same answer. Now, let's do one more practice. Again, I'm gonna take the easy way, which is very easy to do. It's this one. I'm gonna write it over here. So here's the equation. I'm gonna substitute their formulas with their values. So I'm gonna start with this one. I have 2 multiplied by the enthalpy of formation of HNO3. So HNO3, then plus, then NO, which is over here, 90.2. Now, there's an arrow. And then there is 3 NO2, this value, 33.9, and then plus the enthalpy of formation of H2O, negative 285.8. So now we get it on our calculators and we start finding the answers. So for this one, the final answer is negative 2,506 negative 256 kilojoules, let me check, kilojoules per mole. I'm just going to write per mole because anyway, I am going to calculate the standard final one for the reaction. Now, for this one over here, the answer is negative 184.1 kilojoule per mole. Now, in order to find the delta H of the reaction, we do final minus initial. So that is delta H of the reaction, final minus initial. And the final answer is 72.1 kilojoule. Now let's do it in a different way, but we will get the same answer. The different way means that you are going to do the product separately, the reactants separately, and then get the difference at the end. So let me start with the enthalpy of reactants. I have 2HNO3. So for this one, I'm going to multiply it by 2. And I have NO. It is just over here, NO. So negative 173.2 times 2 plus 90.2. Now I'm going to do the one for products. I have NO2 multiplied by 3, and I have H2O. So it is 33.9 times 3 and negative 285.8 times 1. And we are going to get the same answers. So for the reactants, the value is going to be negative 256.2 kilojoules per mole. And for the product, it is going to be negative 184.1 kilojoule per mole. Now, the final answer, the delta H enthalpy of the reaction, it is products minus reactants. And we get the final answer to be 72.1 kilojoule per mole. Now, is the reaction above exothermic or endothermic? Well, we got a positive answer, so it is an endothermic reaction because delta H of the reaction is a positive value. One more example. I'm going to do it now in an easy way. Let me just cover the answer here so that I have some space to write. So let's begin. Here's the equation. I'm just going to substitute the values. Fe3O4. Here's the value. So negative 1118.0 plus CO negative 0.5. Now there's an arrow, and there's a 3, and there's FeO. So negative 272.0, and then plus, and then the CO2. I am substituting the values of standard enthalpy of formation of every compound. Now, I am going to find the sum of this, then I am going to find the sum of these numbers, and then I'm going to find the difference between them. So for this one, it is negative 1228.5 kilojoule per mole. And for this one, over here, it is negative 1209.5 kilojoule per mole. Now, this is initial and this is final. So to find the enthalpy of the reaction, we subtract the enthalpy of the products minus the sum or total enthalpy of the reactants. So the final answer is going to be positive 19 kilojoule per mole. One more question. So this one, the enthalpy, it's a multiple choice question. Again, I'm just gonna highlight here so that I can provide myself with more space. Okay, so here we go. 2 multiplied by zinc sulfide plus 3 by the value of oxygen. Now, 2 and the enthalpy of formation of zinc oxide plus 2 times this one. So 2 negative 296.8. Now let's find the summation of the enthalpy of formation of reactants. So it is negative 412 kilojoule per mole, and for this one over here, the enthalpy of formation of all the products is 196.8. The answer is negative 1290 kilojoule per mole. Now we are going to subtract product minus reactants. So the enthalpy of formation of the reaction is the enthalpy of the products, the final, minus the enthalpy of the reactants, the initial. And the final answer is going to be negative 872.2 kilojoules per mole. So negative 872.2 kilojoules per mole. Now, moving on to topic 1.5. In this topic, you need to know the 3 laws of thermodynamics. The first law is a law that you are very familiar with. It's the energy of the system is always the same. It's not lost, it is not gained, it's just converted from a form to another. So the energy of a system is not lost nor created. It is simply changed or transferred from one form to another. From one form to another. Now, the second law of thermodynamics is also stating that the entropy of the universe is always increasing. The entropy of the universe keeps on increasing. And for the third law of thermodynamics, we say that the entropy of a perfect crystal in a perfect world is 0. Because you will see that the entropy of substances is never 0. It's only 0 if it's a perfect crystal. Now, we reach the part of the questions where you have to indicate the entropy change of a system, if it's going to increase or decrease. Or sometimes they might ask you if it's positive or negative. So, if S increases, if you are comparing two objects and you see that S increased, it means the delta S is going to be positive. If the entropy of a system before to after decreases, it means the entropy change is negative. Always remember that entropy is the degree of randomness, how things became more chaotic, more distributed, more disordered. So all of these means entropy. Now, there are a set of rules that you need to keep in mind. If we are going from a solid to a liquid to a gas, entropy increases. So entropy increases because the particles are more disordered. If temperature increases, entropy increases. If a reaction produced more products, more moles of product than it was before, then entropy increased, and so on. So I'm gonna go with every example. Here, I can see that I have H2O and I still have H2O, but the state changed from gas to liquid, which is more ordered if I want to compare liquid to gas in liquid phase. So in this case, the entropy decreased. So S decreased, or I can say delta S is negative. Why? Because the liquid is more ordered than the gas. Here's another question. I have oxygen plus 4 Fe3O4 solid giving 6 Fe2O3. So here we have to compare. I have a molecule in the gaseous state and the solid state, but now in the product it's only solid. And we know that the entropy of solid is always lower than the entropy of liquid or gases, because the particles in solid are so much highly ordered. Now, even if you counted here, you can find that you have 5 moles, 1 plus 4 compared to 6, but still you have to pay attention to the physical states. So in the reactant, you had 4 compounds, 4 particles of solid. Now you have 6 that are solid. So it became more ordered. So the disorder didn't increase. So in this one, entropy decreased since more solid particles appeared on the product side and no more gas in it. Okay, so solid has lower entropy than gas. And since this is decreased, also entropy is going to be negative. Now, I changed a bit the examples just so that I can explain the entropy sign for you. Now, let's look at this one. I have solid and I have 1 compound. Now, I do still have solid, but I have with it a gas, and what was 1 became 2. So when the number of molecules increases on the product side, entropy increase. So here entropy increased for 2 reasons. So entropy increased because we have more moles on the product side. Also a gas is formed. We had a solid before, and now a gas is formed. So delta S, because it increased, it's going to be positive. Now, one more example, and look at it. I have a liquid, 2 molecules of liquid, and 2 and 3 molecules of gas. Here, 2 molecules of liquid and 3 molecules of gas. Now, what happened? Now I have 2 molecules of gas and 4 molecules of gas. So I had 5, and now there's 6. So S increased because more particles, more moles of gas are on the product side. Now, let's see a different kind of question. So we need to say which one has a higher or larger entropy. A liquid or a solid? Of course, a liquid, simply because entropy of liquids, particles are more arranged than in the solid state. So entropy of liquid is higher than entropy of solid. In liquid, particles are more apart from each other, and slide past each other, While in solid, I don't have space, so I'm going to mention it. In solid, the particles are in fixed positions and they vibrate. Now, another example, solid or an aqueous solution of a salt. Now, when a salt is in the solid form, the particles are packed with each other. But when I put it in a solution, the particles, they dissolve and are distributed. So, which one has a higher entropy? It's the aqueous salt, potassium iodide. So, when a salt or when a solid dissolves in water, particles are not anymore packed together. They become distributed in the solvent, or I can say in the solution. So it is a rule, the entropy of aqueous is more than the entropy of solid. Now, again, liquid or solid, which one has higher entropy? Of course, the liquid, for the same reason mentioned in the first one. Entropy of liquid is always higher than the entropy of solids, because in solids, particles are stacked together, vibrate in fixed positions, so they don't have much space, while in liquid, particles slide past each other. They have more freedom past each other with more freedom. Now, for the last one, I have two molecules of gas. But which one has higher entropy? I will go with the molecule that is more complex. NO2 has one nitrogen atom and two oxygen, while O2 just has two oxygens. So as the molecule, or here, entropy of a more complex molecule, of course, is higher than the entropy of a simple molecule. So you can count the number of atoms in the molecule. You can rely on the mass of the atoms in the molecule. So when I have more atoms in the molecules, entropy increase. So entropy of complex molecule, this is how we say it, is larger than the entropy of simpler ones. Now, let's look at another example. Here I have a mix of molecules, simple, complex, and just an atom. Now, let's start here. We need to order it in the increasing entropy. I know for the fact that this is the most complex one, having 6 atoms, 2 carbons and 4 hydrogens, and this one having 5 atoms, 1 carbon, 4 hydrogens. So C2H4 and CH4. Now that's their order. Now let's look at hydrogen and let's look at neon. Now this is a tricky one. You will think that because neon is a 1 atom, it doesn't have entropy as much as the hydrogen, which is made up of 2 atoms. But the size of neon is this much, and the size of hydrogen atom is so much smaller than the neon. This, if I want to compare their sizes. So the entropy of neon is higher than the entropy of hydrogen. Again, this is an exception. They are comparing a very tiny molecule to a bit large gas. Let's say you don't know about the sizes. You need to compare their mass. Neon mass is 20, you can get it from the periodic table, 20 grams per mole, whereas hydrogen mass is 2 grams per mole. So do you see the difference in the mass? So more mass, bigger size. So definitely neon will have a larger entropy than hydrogen gas. So let's move on to another example. Arrange them in the order of decreasing entropy. So here, that's a more complex molecule, that's a less complex one, and that's the least. Even if I compare their masses, there's a big difference in the mass. Here I have 6 carbons and 6 hydrogens. The mass is 78 grams per mole. This one is 44 grams per mole, and this one is 4 grams per mole. You can compare their mass. You can compare their complexity. So this one has the highest entropy, then oxygen, then helium. So the complexity of the molecule, the more complex, the more disordered it is. Now, let's go back to using the summation equation, but this time in order to calculate the entropy of a reaction. So delta S of the reaction is equal to the summation of the entropy, total entropy of products minus the summation of the total entropy of reactants. So this time we are using entropy. Now, let me do it here in the easy way. So I'm going to copy again the equation, half oxygen and H2O. Hydrogen, 131 joule per mole Kelvin, plus half O2 is given over here, 205, gives H2O, which is 70. Now let's find out the total of the entropy of reactants. The total is 233.5 joule per mole Kelvin, and for this one is 70 joule per mole Kelvin. Now to find the entropy of the reaction, it is always final minus initial, or the entropy of products minus the entropy of reactants. So it is 70 minus 233.5, and the final answer is negative 163.5 joules per mole Kelvin. Okay, another question, calculate the standard entropy change, delta S, for the reaction at 298 Kelvin. So again, we look at the table here, we find that they gave us the entropy for N, for H2 and for NH3. What I'm going to do, I am going to do it in two ways. N2 is 192 plus the hydrogen entropy is 131. So I just simply substitute and I multiply if I have more than 1 mole. And then 2 times 193. So now we calculate the values of the entropy of the reactant. And this is going to be 585 joules per mole Kelvin. And for this one is going to be 386. Now, to find the delta entropy change of the reaction, we do the entropy of product minus the entropy of reactant. And the answer is negative 199 joule per mole Kelvin. Now again, I can make it in a different way. So once you look at the equation, the minute you look at it, you highlight the reactant, the products. So here is NH3, and I must multiply it by 2 because there's 2 here, 2 moles. And here are the reactants. They are over here. And for these reactants, I need to multiply the hydrogen by 3. Now, let's find the entropy of product. So it is 193 times 2, and that is 386 joules per mole Kelvin. And let's find the entropy of reactant, their sum. So it's those 2. So it's 3 times 131 plus 192, and that is 585 joules per mole Kelvin. You choose the way that suits you better. So that's entropy of the reaction. It is the products minus the reactants. And here's the final answer. Moving on. Free energy, the Gibbs free energy. So the free energy is, the symbol of Gibbs free energy is the G, and that is the energy available to do the work, which is to do the reaction. So it's the energy available to do work. What do I mean by work? It means the reaction to occur by itself, the reaction. Now, usually, the unit of G is the kilojoule. Now, if we are talking about a standard Gibbs energy, Gibbs free energy, the unit is per mole. Now, how do we understand the Gibbs free energy? There is something that you need to know, that delta G is related to delta H, the 2 driving factors of a reaction, the enthalpy and the entropy. So the sign of delta G will identify whether the reaction is going to be spontaneous or non-spontaneous. So if we calculated delta G and we obtained a negative value, it means that the reaction we are looking at is spontaneous. And if we calculated delta G and we got it as a positive, it means it is non-spontaneous. There are times that you can recognize whether delta G, the Gibbs free energy, is spontaneous or not, is positive or negative, depending on the sign of delta H and delta S. So, whenever delta H and delta S are opposite to each other, in the case of exothermic reaction and a positive or an increasing entropy, the Gibbs free energy is always spontaneous, no matter what was the temperature. So always spontaneous. Now, if I have a positive enthalpy with a decreasing entropy, this case of endothermic reactions, the reaction is never spontaneous. Now, the last two cases are simple and it's easy to memorize them. Now, when delta H and delta S both are negative or when both are positive. In the case of negative and positive, or in the case where they have the same sign, delta G is spontaneous, but this depends on temperature. Depends on temperature. So memorize it that way. For an exothermic reaction, a decreasing entropy, so when both are minus minus, the entropy, the Gibbs free energy is spontaneous at low temperatures. So the temperature must be low so that delta G can be negative. And when both of them, the delta H and the delta S, are positive, the Gibbs free energy is spontaneous, or the reaction is spontaneous, but only when the temperature is high. Okay? Now, let's continue for this question. I'm going to erase this just to provide space and solve this question over here. Here I have a table of 3 reactions, X, Y, and Z. And the question gave me the enthalpy of each reaction. As you can see over here, this is an exothermic one, and this is an exothermic one, and this is endothermic. Now, before we continue and specify which one is spontaneous and which one is not, let's put a table and think about the delta S, the entropy. Okay? So, here I have all of the molecules given are gases. So let's count. 4 plus 6, that's a 10. 4 plus 5, that's a 9. It means that the number of moles is increasing, so entropy increases, then it is positive. Remember, when the delta H and the delta S have opposite signs, the case of exothermic is forever spontaneous at all temperatures. Now, let's continue to the second one. I have a gas and I have a gas, and this is a gas. So the state is not going to help me. Let's count. I have 3 dropped to 2. So the entropy decreased over here. And when both are negative, delta H and delta S, this reaction is spontaneous only at low temperature. Now, for the last one, I have an endothermic reaction. Endothermic means that this is positive. Now let's count. 6. Oh, here I have solid, but the solid turned into gas and solid. Also, 6 moles of solid, it turned to 4 moles of solid. So it's becoming more random, more disorder. Specifically, I have less solid and I have more gas. So here it is increasing. Well, by the way, when both of them are positive, the reaction would be spontaneous at high temperatures. Now, let's read and finish this question. Which one is spontaneous at all temperature? X, because it is an exothermic reaction with an increasing entropy. So that's the answer. Now, consider the reaction Y. They gave me delta S negative 150. Yes, we also assume that delta S is negative. Now they want us to calculate the delta G and the temperature is given. Now, let me first put the formula. Delta G is equal to delta H minus T delta S. You need to note that if temperature was given in Celsius, you must convert it to Kelvin by adding 273. Now the temperature is already in Kelvin, we don't have an issue with it. The delta H unit must be the same like delta G, or when you calculate the delta G, the unit of delta G will be the same as delta H. Now for delta S is always given to you in joules per mole Kelvin, whereas delta H is kilojoule per mole, and the delta G is going to be kilojoule per mole. So before you start solving, you must know that delta S must be always divided by 1,000 to convert it into kilojoule per mole Kelvin. So let's start our substitution. This is negative 120. There's a minus in the formula. This is for temperature and this is for delta S. 298, and the delta S is negative 150 over 1,000. You always have to remember to divide it. So the unit is going to be minus 75.3, and the unit of delta G must be like delta H, kilojoule per mole. Now, which one is endothermic? Endothermic is the one having positive delta H. So I select from the table the positive delta H, that is Z. Which one has a decrease in entropy? It means which one has a delta S negative? That is Y. When a reaction is spontaneous at all temperature, we just mentioned this, it is X, and a reaction is spontaneous at all temperature when it is exothermic, meaning delta H has a negative value, and with an increasing disorder, randomness, entropy. It means when the entropy is positive. In this case, the reaction is forever spontaneous. Now, the last question in this topic, 1.5, calculate the free energy delta G if this reaction is at 25 degrees Celsius. We look here, the delta H is given to us, and the delta S is given. As I said in this formula, delta G equal delta H minus T delta S. This must be in Kelvin. And the delta S must be converted to kilojoule per mole Kelvin. And these two will have a unit of kilojoule per mole. So let's start here. Delta H is okay. So let me write here. Delta G is equal delta H minus, here's the formula, delta H minus T delta S. So minus 4.8. And then this temperature must be converted to Kelvin. How? By adding 273 Kelvin. So it becomes 298 Kelvin. Now the delta S must be divided by 1,000. You cannot use it and it's not yet converted to kilojoule. This has to go to kilojoule. So over 1,000. So 60 over 1,000. By doing this, I got an answer of negative 22.68 kilojoule per mole. Now the question is it, no, that's a different one. Oh, that's a different one. Here's question, so that's the answer for question 53. Now let me provide space for question 54. When a reaction is non-spontaneous at all temperature, which means when a reaction is never spontaneous. A reaction is never spontaneous if the delta H is positive. It means an endothermic reaction with a decreasing entropy. with a decreasing entropy. Reaching the last part of our focused questions, topic 2.1. This topic talks about the reaction rate, which means the speed of the reaction. And this means the speed of the reaction in consuming reactants or the speed of the reaction in producing the products. So let's begin with the first question. How do you calculate the average reaction rate? So we measure the rate of consuming reactants over time, or we measure the rate of producing products over time. So the average reaction rate could be calculated by using the concentration change of products over the time, or the consumption of reactants, concentration of reactants over the time, the change of time. Now for reactants, we always add the negative sign because reactants are consumed. So in this question, it's the correct choice is B, by dividing the change in concentration, whether reactant or product, by the change in time. The formula for calculating the average reaction rate is rate delta concentration over delta time, where delta, and this delta stands for change, and more specifically, anything final minus initial. So if you are dealing with concentration, final concentration minus initial concentration. If you are talking about time, final time minus initial time. Consider the reaction X plus Y giving W. If the concentration of Y at 6 seconds is 1 molar and at 25 seconds it is 0.46 molar. Before you begin solving, you need to check if Y is a reactant or a product. You can see the location of Y, it's on the reactant side. So Y is a reactant. Moreover, when you check the concentrations, it started 1 and it finished at 0.46. So the reaction, the concentration is decreasing. Therefore, and also the question is, it says, find the rate of disappearance. So the average rate of Y is negative delta concentration of Y over delta T. I chose the minus because I see the values decreasing. Also, I can see that Y is a reactant. Also, they mentioned in the question disappearance. So, final minus initial. Final minus initial. And this is the final time minus the initial time. And the answer is going to be 0.028 molar per second, or you can write MS minus 1. If the concentration of a reactant A decreases from 0.8 mole per liter to 0.4 mole per liter in 5 seconds. Here, they didn't give me the beginning, the time at the beginning and the time at the end. They simply gave me delta T. So they want to find the average rate. So the average rate of this reactant is going to be 0.4 minus 0.8 over delta T, which is 5 seconds. And the final answer is 0.08 mole per liter second, or I can write molar per second, or MS minus 1. If the concentration of a product W, now we're talking about a W, it's a product. So when I write the average reaction rate, I will simply put delta W over delta T. So the product, they want to calculate the average rate between 2 seconds and 10 seconds. The concentrations are 0.5 and 0.9. Look at the concentration, it is increasing. So definitely this is a product. Final minus initial, and this is 10 minus 2. So the final answer is going to be 0.05 molar per second. Moving on. Compare the concentrations of the reactant and products during a chemical reaction. This is a very important question. Expect something like this in your exam. I'm gonna explain it on a graph and also in words. So here's the concentration versus time. Reactant, we have reactant at the beginning. So we have a certain quantity that is going to be consumed over time. So the reactant during the course of the reaction is going to decrease, and this is how it is represented by this graph. Whereas the product, it's going to be produced. So at time 0, we don't have yet B formed. So B is going to start forming and it increases over time. So this is for product that increases with time, and this is for reactant that decreases to give me a product with time. Explain the two conditions according to the collision theory that must be met for a collision between reactant molecules to be effective. For a collision to be effective, first of all, the reactant particles or the substances, the reacting substances must collide. So the reacting substances first, they must collide. And when they collide, they should collide with sufficient energy. And when they collide, the collision, where they collide, they hit with each other, they bump with each other, it should be in the right place. So when they collide with sufficient energy and correct orientation. So these are the conditions for the collision to be successful. So again, these are also called assumptions. So the assumptions of the collision theory are 3. 1, substances, the reacting substances must collide first. Again, the reacting substances must collide with sufficient energy. Now, the substances, the reacting substances, must collide with sufficient energy and correct orientation. Orientation, and I mean by this, the place where they hit must be in the right place for the bonds of reactants to be broken in order to form new bonds. And now we reach what we call the activated complex. If I look at an energy diagram, whether the reaction is endothermic or whether the reaction is exothermic, the reacting particles, the reactants, must have sufficient energy, which is the activation energy, for them to reach what we call here at the top of the curve the activated complex. So at this point, this is the activated complex. So here, this is the activated complex, and the energy needed to reach the activated complex, it's from the enthalpy of reactant to the activated complex. This is called activation energy. So activation energy is the minimum amount of energy that reacting particles must have in order to reach and form the activated complex. So what is an activated complex? An activated complex is simply a transition state. It's a temporary arrangement where the old bonds are being broken, and at the same time new bonds for the products are being formed. So it's just a transition state that is going to move the reaction from reactant in order to form the products. Now the last most important part is topic 2.2. Topic 2.2, we deal with what we call the rate law. So again, we are still talking about the speed of a chemical reaction, but we are using a different formula, something determined experimentally. So the rate law is equal to a K, which is a specific rate constant multiplied by the reactant of a reaction, the reactants involved, and the reactants are raised to a certain power that we call order. Now, this K is a constant. When concentration of reactants change, when concentration of reactants change, K remains constant, unchanged. The only thing that allows K to change is the temperature. Only when temperature changes, K will change. So under what circumstances the specific rate constant K is not constant? When the temperature changes and not the concentration of reactants. Now this K is specific for every reaction, and the unit of K changes depending on the overall order of the reaction. So if the reaction is zero order or first order or second or third. First, let me give you the formula of the rate law for a zero order reaction. A zero order reaction, it means that the reactant is to the power of zero. And if it is to the power of zero, I can simply write R equal K. And this is the only case where where K, which is the specific rate constant, has the same unit of the rate of the reaction, which is molar per second, or I can write it ms minus 1, or I can even write mole per liter second. Now, if the reaction is first order would look like this. R, I'm going to change the color of my pen. R is equal K, and A would be to the power of 1. In this case, the unit of K is just per second, or S minus 1. Now, if the reaction is second order, what would be the formula of the rate law? So K would be, R would be K times A squared. Or even if I have two reactants, it would be A to the power of 1 and B to the power of 1. We are still dealing with second order. If we have two reactants, each one will be 1. If I have one reactant, the order of a second order, it would be 2. So what would be the unit of K? It's going to be per molar second, or M minus 1, S minus 1, or L per mole second. Now I'm going to clarify this. Molarity is mole per liter. Now if I write M minus 1, it means this is the inverse of M. So you can reverse L per mole and write L per mole. Now if I have a third order reaction, how will the formula look like if I have a third order? So K equal A to the power of 3. or maybe R equal K, A to the power of 2 and B to the power of 1. Or maybe I have 3 reactants ABC, 1, 1, 1. So as long as the total sum of the orders or the powers is equal 3, the overall order means is the third order. So what would be the unit? It is per M2S or M minus 2 S minus 1 or L squared per mole squared S. So you should memorize these units. Now let's continue. Write the rate law for a reaction involving A and B. So I have a rate law K, A, and B. I don't know yet the orders, but I'm going to continue my sentence. Where the reaction is second order in A. Second order in A means that I'm going to write here number 2. And first order in B, it means that B is to the power of 1, or you can simply just write B. So this is the rate law formula. Another question. Determine the rate law for the reaction A plus B, giving C and D. Now, when we're doubling A, only quadruples the rate. So, if A doubles, the rate is going to quadruple. This means that A is second order. So, in this formula, R equal K A squared. Now, let's continue to see the B. And doubling B doubles the rate. So if B doubles, the rate doubles. This means that the B is first order. So here is the formula of the rate law. And the overall order is 2 plus 1. That's a third order overall. The rate law can be written as rate equal K times the concentration of A, where A represents the concentration of the reactant. What is the order of A? Because it's written this way, A looks to be first order. If there is a 2 next to A, I would say A is second order. If there's a 3 next to A, I would say that A is third order. If I don't see A in the formula and I know that A is a reactant but I don't see it, it means A is zero order. If a reaction was found to be second order in carbon monoxide, so here's a reaction, second order in carbon monoxide. Concentration, the rate of the reaction, what would happen to it if CO doubled? If I have a second order reactant and it doubled, the rate will quadruple. If I have a second order and it was tripled, the rate will increase 9 times. But if CO was first order and I doubled it, rate will double. I tripled it, rate will triple. Now, let's now use the method of initial rates to find out the rate law of a reaction. Now, when I want, so first before, I'm just gonna write the general formula of the rate law. How does it look like? So A is to a power of X that I don't know yet, and B to the power or order of Y that I don't know yet. So now let's find the order of A. If I want to find the order of A, I need to choose the trials, the experiments. So I look at where was B constant. B was constant in trials 1 and 3. So in order to check the order of A, I need to make B constant and study the changes happening to A so that I can determine the rate of A. So I am going to take trials 1 and 3. So what's going on to A? When A was tripled, or I would say 0.819 over 0.273 raised to a power of x, the order jumped from 2.83 to 25.47. Upon calculating this, I'll find that x is 2. Now, let's see, or let's find the order of B. So, in order to study the order of B, I need to choose the trials where A was constant, so that I can understand what did B do to the rate. So, in this case, I am going to take trials 1 and 2. So, trials 1 and 2, when B was doubled, trials 1 and 2, so when B was doubled, the rate stayed the same. So, I can write it like this: 1.526 to the power of y, the rate did not change. And this means that B is 0 order. So what would be the rate of this reaction? That's it, because B should not be here. It is 0 order. What is the value of the rate constant K? In this case, since now you know X to be 2 and B 0, now I can use this formula to calculate K. I can go with any trial that I want. So I'm going to choose the first trial. R equal 2.83 equal K multiplied by the concentration of A raised to the second order. I'm not going to add B, because if I put it, it's still going to give me 1 because it's to the power of 0. Therefore, K is 37.97. Now, since this is second order, the correct unit of K must be m-1, s-1. Now, they gave me another question. Again, I'm going to write the same formula to keep it in front of me. B is 0. Again, I can cancel out B because it's 0. Now, they want me to calculate R if A was 1.6 squared. Don't forget the order of A. Now, because now we calculated K in the previous question, now I can use it over here to find the rate. And the rate is going to be equal to 97.2 molar per second. You can check on my channel the video of the rate law for more practice and details about this topic. In a laboratory session, 2 groups of students, group 1 and 2, performed a set of experiments to investigate the rate law of the reaction given above. Before I start reading, I'm just going to write a general formula for the rate law of this reaction. So I'm going to write L, X, and Q, Y, because I don't know yet their order. Group 1 says, when the initial concentration of L was doubled, the rate doubled. So L doubled, rate doubled. We're still doing the same. L doubled, rate doubled. It means that L is first order. When concentration of Q doubled, the rate did not change. It means that Q is 0 order. Now again, let's read the findings of group 2. When the initial concentration of L was doubled, the rate was doubled. Yes, that's correct. So again, another indication that indeed L is first order. Now, when the initial concentration of Q was tripled, the rate did not change, stayed the same. So Q is 0 order. So Here's the final formula of the rate law of this equation, L. That's it. I don't have to put Q because Q is 0. And the overall, the total order is 1. So here write the rate law, K, L. Now, moving on to another question. Here I have two reactants. So I'm gonna write the overall formula. I'm gonna start from here, K, NO2 minus to a power that I don't know yet, and NH4 plus to a power that I don't know yet. Now I'm gonna read A to find this number. I'm gonna solve B to find this number. Then deduce the overall order. Once I have those numbers, I'm gonna add them over here. Now let's start. Experiment 1. When the initial concentration of NO2 minus was increased from 0.2 to 0.4, 0.20 to 0.40, it means when NO2 minus doubled, the rate doubled. So the rate doubled. This means that the order, or it is first order. So NO2 minus is first order. Now I can erase this and I know it. It is just 1, or I don't have to write it. Or I don't have to write 1. Now let's continue. So here I know that this is 1. Let's move on. When the initial concentration of NH4 plus is increased from 0.03 to 0.060, 0.030 to 0.060, this means, they mean by this, when NH4 plus doubled. When NH4 plus doubled, again, the rate doubled. The rate doubled. So it means that also NH4 plus is first order. So now I know that this is first order. So the overall order is 1 plus 1. It is second order. And that's it. All the best in your exam.